Now let's start to talk about one basic way of solving equation sets, which is Gauss elimination. This slide shows the graphic method to solve a small set of equations. For example, solve x1 and x2 with two equations. Then we can draw two lines regarding the two equations, and the intersect is the solution for x1 and x2. The right-hand side of this slide shows three EO-conditioned systems, where it is difficult to identify the exact point at which the lines intersect. The first two cases tell us that the system is singular, and the third is near singular and extremely sensitive to round-off error. Besides graphic method, there is a rule called Cramer's rule, which is used to solve up to three equation set system. To solve x from a set of three equations, where the A matrix is 3 by 3, we can follow the Cramer's rule, where we calculate each element in X. The first one is x1 as the ratio of two determinants. The denominator is D, which is the determinant of the original A matrix. For those of you who are not familiar with determinants of matrices, please refer to the textbook chapter 9.1. And the numerator is the determinant of a new matrix formed by the B column vector and the second and third columns of matrix A. Similarly, we can calculate x2 and x3 and solve this equation set. However, it is difficult to calculate for larger matrices. To solve equation problems with more than three equations, we need to explore other ways. And here we introduce one of the most basic ways, which is called naive Gauss elimination, which involves two phases. First phase is forward elimination. Second phase is back substitution. And the word naive means we suppose non-zero parameters for all elements in matrix A. Think about the hand solution of equation sets. First, the equations will be manipulated to eliminate one of the unknowns from the equations. And the result of this elimination is that we have one equation with only one unknown, xa. Consequently, this equation could be solved and the result back substituted into one equation containing the solved unknown xa and one other unknown xa minus 1, so that we can solve for xa minus 1. Continue this so that we can solve all the unknowns up to x1. Gauss elimination is one of these basic methods that follow this scheme for solving large equation sets. In Gauss elimination, we prepare a matrix by concatenating matrix A and vector B, which is shown in the upper right of this slide. The forward elimination step is designed to reduce the set of equations to an upper triangular system, which is shown as the matrix under the original concatenated matrix. Some of you have already known how to do this reduction in matrix form, but in the next slide, we will still show how this step is calculated. The back substitution step is to solve for xn to x1 by calculating xn first. In this specific example, x3 first, based on the last row of the upper triangular system, and then x2, in the end, we solve x1. Following the same procedure, we can cancel x2 item in equations 3, 4, all the way to n. In the end, we will see the original equation set to be updated to this new equation set. Now we can solve xn by simply calculate the last equation. We can substitute xn to the second to the last equation, then we can solve xn minus 1. This is how Gauss elimination method solve our problem. If we write the equation set with matrix and vectors, you can see matrix A is now an upper triangular matrix. Since vector B will change tremendously due to the multiplications and subtractions, it is required to concatenate A with B, so that all changes in the equation set are shown in one matrix. This is the Gauss naive function and file. Inputs A and B are the matrix and vector from the original equation set, and output X is the solution of the equation set. At the beginning, check the matrix A, which must be a square matrix, and generate a new matrix AUG by concatenating matrix A and vector B. In the forward elimination step, we use a nested for loop to make the upper triangular matrix. There are two lines to be executed in each loop. First, divide AUGIK by AUGKK so that we can normalize the coordinate of xk in the ith row and to make it identical to the kth row by multiplying with a factor. Then we do the subtraction of the two rows to make AUGIK equals 0. In the end of this whole nested for loop, the lower triangle of matrix A becomes all zeros. In the back substitution step, we first define x to be a zero vector of length n. This is memory pre-allocation based on lecture 2. Then we solve xn by a simple dividing based on the last equation. Then we use a for loop to solve xi from xn-1 all the way to x1. You can see a simple demonstration of generating this function and call to use this function in an example of solving a 3x3 matrix or a 3-equation system. Now we explore a little bit about the time complexity in executing naive Gauss elimination. Addition, subtraction, multiplication, and division are all elementary operations. By counting how many elementary operations one method has, we can evaluate the time complexity of the method. The time complexity of naive Gauss elimination is 2/3 of n cubed plus upper bound of n squared plus n squared plus upper bound of n. N is the dimension of the A matrix. In this time complexity analysis, n cubed plays a major role because it has the highest power. As the system gets larger, the computation time increases greatly because of this n cubed item. We can also see that most of the effort is incurred in the elimination step. You are not required to know how to calculate the time complexity. This slide just wants to show that the elimination step takes most of the computing time. In the previous slides, we talked about naive Gauss elimination, where we suppose there's no zero or close to zero parameters involved. Otherwise, we cannot divide. However, if there are zero parameters, we need to switch rows and columns by using permutation, and this is called pivoting. The goal of pivoting is to have the element with the largest parameter in the pivot position. So what's the difference between non-pivoting and pivoting? Here is an example showing the original equation set with 0.0003 as the parameter of x1 for the first equation, which is supposed to be used for the second equation to match through multiplication. But 0.0003 is a close to zero number. If we consider significant figures, which is related to the computing complexity, we can see that with fewer significant figures, we cannot obtain the correct results because of the significant error. To obtain x1 with an acceptable error, we need to use 6 or 7 significant figures. As a comparison, if we do partial pivoting, which is to switch the order of the two equations, with only 3 significant figures, the absolute value of percent relative error for x1 is already the same as using the original equation set and 7 significant figures. Let's look at one benefit brought in by Gauss elimination, which is that it immediately provides the determinant of a matrix by calculating the product of all diagonal elements. If pivoting is added, then the equation for the determinant calculation has a -1 to the power p item, where p is the number of times of row permutation. There is one type of engineering problem in which the parameters are in a tridiagonal matrix like the following, which is also a band matrix. It is actually an easier case compared to the regular equation set system because you eliminate much fewer items in the forward elimination step. It is a sparse matrix, which requires a lower computing complexity.